Hello, geometry. Alright, so in this video I'm going to go over chapter 5, section 3, angle bisectors of triangles. First of all, we're going to look at angle bisectors in general. An angle bisector is a ray, particularly a ray, that divides an angle into two congruent adjacent angles. So if you have this larger angle, the angle bisector is the ray that cuts this larger angle exactly in half. Okay, so in this case, PS, ray PS, is the bisector of QPR. And the distance from S to PQ, so the distance from a point on this angle bisector, so the distance from that to PQ, this side, is going to be the same as the distance from it to the other side when hitting at a right angle. See how there are right angles here? So an angle bisector will cut the angle exactly in half, essentially. Here's the theorem for that. If a point is on an angle bisector that is equal distance from the other two sides of the angle, that's what I was just describing. So it's going to cut the angle in half, and if you draw a line to each side at a right angle, so it meets at a right angle to each side, this is going to be the same length. CD is going to be the same length as BD. Okay, so the converse is also true. If you happen to know that BD is equal and CD is equal, if you happen to know that they're equal to each other, then that would tell you that segment, or I should say ray AD, is an angle bisector of BAC or CAB. So two ways you can go about this, or two things that you could be given. You could be told that it's an angle bisector, and it gives you that these two segments are equal. Then you can conclude that. Sorry, let me start over. You could be told that it's an angle bisector, and thus conclude that these two segments are equal, or you could be told that these two segments are equal, and therefore it must be an angle bisector. Okay. Example 1. Here we go. GFH is the larger angle. We want to find the measure of GFJ. Okay. Now, we can't just assume that this is an angle bisector because it kind of looks like it is. We have to actually know for certain that it is, because it could just be off by 1/10 of a degree, and then it's not. Well, they told us that this is 42, so if this happened to be an angle bisector, that would be easy because these have to be equal. So how are we going to conclude that it's an angle bisector? Well, first of all, we know that JG is perpendicular to this side, FG, and we know that JH is perpendicular to this side, FH, and they told us that JH and JG are both 7 and thus equal to each other. Therefore, by the converse, we know that JF is a bisector. And since JF is a bisector, then GFJ, lots of letters here, GFJ must be equal to HFJ, and therefore GFJ, which is what I was looking for, is 42 degrees. Done. Alright, here's an example that has a figure. It says a soccer goalie's position relative to the ball and the goalposts forms congruent angles as shown. Will the goalie have to move further to block a shot towards the right goalpost R or the left goalpost L? Okay, let me bring this solution up here. Well, if these two are equal, okay, then congruent angles indicate that the goalie is on the bisector of LBR by the angle bisector theorem, the goalie is equidistance from side BR and BL, so the goalie must move the same distance to block either shot. If he is in the center, then it'll be the same distance. Okay. So here we have one of these algebraic problems that you see a lot of. For what value of x does P lie on the bisector of A? So for what value of x will P lie on the bisector? And that'll only happen when these two, when BP and CP are equal. So we want to find the x value that causes those to be equal. So we're going to set them equal to each other and find what x value causes those to be equal. Solve this, subtract 2x from both sides, we get negative x plus 3. Subtract 3 from both sides, you get negative 4. Multiply both sides by negative 1, or just drop the negatives, however you want to do it. You get x equals 4. That's the answer. One more thing here, and we'll be done with this video. Going back to triangles here, a couple more definitions. Congruency of angle bisectors in a triangle. The angle bisectors of a triangle intersect at a point that is equidistant from the sides of the triangle. So what will happen here is if you take all the angle bisectors of a triangle, okay, so this is the red lines are the lines that cut to each side or each vertex and each angle, I should say, for each vertex in half and extend those. They all meet at the same point. So that's another set of concurrent lines or rays, and they meet at a point whose distance from each side is the same. So another equal distance point. So the distance that point is from each side meeting at a right angle will be the same value. So this is called the in-center. That's what this definition down here is. The in-center is the point of concurrency of the three angle bisectors of a triangle. So this in-center right here. And it's equal distance from each sides, and it's found by taking the angle bisector of each angle. Example 4, let me just move this up. In the diagram below, N is the in-center of triangle ABC. Find the distance ND. So distance ND would be the same as NF and same as NE, but we're not given NF or NE. Okay, we're given NA. It's not going to be exactly 20. Or we're given AF. It's not going to be exactly 16 though. However, if it is congruent, if what we're looking for ND is congruent to NF, what we have here is a right triangle with a hypotenuse of 20 and one of the legs 16, and we want to find the third leg. So we can use that fact that if we can find NF, then we will know that ND is the same value. And we're going to use Pythagorean theorem on these two values to find what NF is. Okay. So 16 squared plus unknown squared equals 20 squared. 16 squared is 256. 20 squared is 400. Subtract, you get 144. Take the square root, you get 12. NF is 12. ND then is 12. So using the fact that it's an in-center, we can find that measure. So again, bookwork, work packets that go along with this. Fun. Thank you, and have a good day.